In previous lecture, we've been talking about equation for planes, equation for lines. Okay. In last lecture, we had example on the cat and mouse problem. Okay. And that particular problem, the issue I want you to focus on is basically for a line equation, how do you differentiate between the pure mathematical meaning and a physical meaning, okay, when it relates to velocities. Okay, so that's the key points for that particular question. So to better illustrate this thing here, I have programmed a little MATLAB file here. I wonder if you can see it clearly. Basically, we have the cat and mouse equations entered, okay, over here and here, and then we want to check if this cat's going to catch the mouse or not. This one here is the original one, right? It's the original one. So there are a couple of conditions, so let me comment this one first. Okay. So as you can see, based on if I run it, so this is the original question. I believe this is the cat, this is the mouse. As you can see, they don't catch each other basically, right? The blue dots doesn't intersect these red dots. And when we change the cat velocity, if you remember in the last lecture, when we change the cat velocity, this is the old velocity 2, 3 here. So we changed the cat velocity after some calculations, right? So now, if I run it again, big one. So that does catch there, right? So that's the basic meaning here, okay? So I'll upload this one to the, I think it's already uploaded. So you can play around with it just to catch the physical meanings that are here for line equations, okay? Yeah. You can also think about how do you extend the similar problem to 3D situation. Okay. 3D basically means consider the trajectory in 3D space. How do you determine whether the cat is going to catch the mouse or not? Okay. Yeah. So I'll go over an example, okay, and then we'll look at a little summary at here. Okay. And then I'll move on to a new topic called parametric equations and vector functions. Okay? Yeah. So let's look at an example over here. We have a plane x plus 2y plus 4z equal to 7. Okay. So this is the plane here. I got 2 points, Q0, Q1. Okay, so I got 2 points at here. Now the question is, okay, the 2 points are what are the relative position of the 2 points, okay, with respect to the plane? Okay, with respect to the plane. So of course, you can imagine if you have plane, you get 2 points, then maybe the 2 points on the same side, okay, or opposite side. Okay. Or maybe one is on the plane. Or you can decide, okay, or some other general relationships, right? Yeah. Okay, so when you have this kind of question, what kind of logic way of thinking shall we do with respect to this question to figure out the relative positions? Okay. Yeah. Oh, the easiest one actually maybe. It says one is on the plane, right? how do we know whether the point is on the plane or not? Exactly. So no matter what we do, I guess the first step we do is we substitute this Q0 or Q1 into this plane equation here. Let's just see what happens, right? Yeah. So we substitute only to the left side though, huh? Only substitute to the left side. Okay. Substitute into the plane equation. And we got, let's say for Q0, okay, for Q0, if I substitute the left side, what is that equal to? So -1 over here, plus 2 by 2, plus 4 by 2, and that gives us a value which is 4, 8, 12 minus 1, 11, right? So 11. So 11 does not equal 7, so that means that point is definitely not on the plane. Okay? Yeah. And for this Q1 point, your left side, 1, 2 by 3, 4 by -1, and that equal to 6 plus 1, 7, minus 4, is 2, right? So 2 is not the same as 7, so that means this point is not on the plane either, and it's less than 7. So now you can make a decision based on this condition in here. So what does that mean by 11 greater than 7 or 2 less than 7 at here? Yeah.
Wouldn't it be 3?
Oh, it's 3? Oh yeah, 3. Still less than 7. So what does that mean at here? Oh, in the opposite side. Okay, good. Now, basically, the question actually can be rephrased like this. Geometrically, see, this is the plane, the left side here. This is the plane, right, on the left side. So when you say if this is a plane greater than 7, or this is a value less than 7, and the middle is equal to 7, right? So that's the 3 conditions. So basically, if let's say illustrate the idea, maybe I have a plane like this, okay? If I plane like this, and this is the plane for this one here, okay, for the equal, okay? So when you see this plane, or when you see this expression is greater than 7, so physically, where do we actually pointing to in this 3D space? Where does it refer to for the first one here? Plane is infinite, right? Plane basically separates the 3D space into the top and the bottom, right? The two parts. Then if this guy is greater than 7, basically refer to which portion? The top. Okay? Yeah. So that refer to the top. And this one refer to the bottom here. So any points beneath that plane. Okay? Yeah. And given the 2 points satisfy the condition, essentially maybe Q0 is over here and Q1 is over here. Okay? Yeah. That's the physical concept behind the greater signs or less signs. So similarly, okay, I won't do it now, but you can take a look at lecture notes, or you can think about yourself before look at lecture notes. So then the question is probably if you connect Q1 and Q0, because apparently Q1 Q0 are not on the plane, okay, and chances are Q1 Q0, okay, in this case because on the 2 sides of the plane, so when you connect them, and they will definitely intersect the plane at a certain point, right? Yeah. So the question here is, how do we calculate that intersection point? Okay, so think about this question. I won't do it today, okay, at here. Yeah, but you should think about the question. So good? Yeah. So, to summarize, okay, yeah, I think some people asked the question here. I can see now. One thing I have emphasized when I was talking about plane equation and the line equation. So let me emphasize here a little bit again before I summarize. If you're going to construct a plane equation, what are the two information that you need to find out? Point on the plane, and what? A normal vector to the plane. Okay? Yeah. Or the other way around, if you're given a plane equation, then you can immediately strap two information. One is a point on the plane, the other is a normal vector. Okay? Yeah. Similarly, if you're required to construct a line equation, what are the two information that you need to find out?
Point on the line, vector parallel to the line.
Yes, a point on the line and the parallel vector to the line. Okay, so that's basically that's two simple rules in terms of this plane and line equations. So the two simple rules, that's what you need to stick to. Of course, how do you find this information? That's a different story, right? That you probably need to use a dot product or cross product, anything, right, relates to it. But always remember the simple rules for this, for the planes and lines. Okay. Yeah. So let me summarize just a little bit here regarding what are the possible questions on lines. So if you're required to find line equation, then you look at the question, what conditions are given? You're probably giving a point. So that means you already have a point on the line, okay, and a vector, okay, parallel to the line. So that's the simplest condition. So you have the point, you have a vector parallel to the line. You can immediately construct the line equation, which is r of t equal to r naught plus t or s times the v, right? That's what happens. Okay? Yeah. Sometimes may not be that straightforward. You're probably giving a point, okay, and a parallel line. Okay? So you have a point and you have another line that's parallel to the line you're looking for. And how would you find the line you're looking for? Right? So that's actually quite easy, because a parallel, when you get the line there, you can extract the parallel vector off the line, and that parallel vector can be used as the parallel vector you're going to use to construct the line equation. And given 2 points, okay, given 2 points. See, that's the question like this one here. You have 2 points. If the question asking intersection point, but I guess you probably want a line equation first, right? From the 2 points. So how do you construct a line equation based on given 2 points? Or it could give you as 2 planes. Okay, so more precisely, we should say it's the 2 intersecting planes, because if the 2 parallel planes, you're not going to get a line, right? Yeah. Or you're given a point, okay, and the line, okay, is perpendicular to 2 vectors. Okay, so the question said the line passed through a certain point, and the line is perpendicular to 2 vectors. So that's actually one of the assignments kind of question. And you're given the point, and the line is perpendicular to a plane. Okay, to the plane. And that's also a kind of assignment question, right? So those are possibilities regarding finding line equation. Okay, yeah. Now usually we don't do that kind of finding line equation predicting exam. That's sort of an easy approach. We make use of one of step here for some other applications. So for example, the kind of question relates to line is like assignment question. What's the distance from a point, okay, to a line? Okay, yeah. Very similar question like a plane. What's the distance from a point to a plane, right? The way to solve this, I can put a plane in here. The way to solve this kind of question from point to a line or plane are essentially the same idea, same approach. In the second lecture, I presented 3 different approaches. You can check out the lecture notes. Okay, and then it's the kind of question I just left you with. What's the intersection point, okay, between a line and a plane? Okay, so if you have the line and the plane out, how do you find the intersection point between these two, right? Yeah. So think about this here. Okay. And the last point I will make is, how do you find intersection point given 2 lines? Okay, yeah. So the question gives you 2 lines and asks you to find intersection points. Okay, intersection point. Now, when this kind of question gives particular last one here, okay, it's always established a certain general sense of geometry. If you have 2 lines in 3D space, the first step for you to do is you probably want to check if they intersect or not, right? Yeah. And the simpler case, they don't intersect when the 2 planes are parallel to each other, 2 lines are parallel to each other. So checking out the parallels between the 2 lines are easy. You just have to look at the parallel vectors. Okay? Yeah. But even if the 2 lines are not parallel to each other, they may not intersect each other. Because why? Because they could be in this kind of structure. Okay? So which means we call this as a skewered. Okay? So one of the assignment questions is skewered. Okay? Only when this happens, right, they intersect each other. Okay? Yeah. Okay, so think about this thing here. So now let me ask you a question here, okay? We don't need to solve this question, but just a general way of thinking here, okay? So let's say suppose a line, okay, goes through a point P naught, okay? Point P naught. And perpendicular to a vector, okay? Perpendicular to a vector. Okay. So I want you to answer is, will the solution for this line be a unique solution, or you could have multiple solutions? Can you illustrate that? Okay. Can you illustrate that? It's just general. Okay. Will solution be unique? Okay, why? Okay, illustrate that. Try to illustrate. Okay, so when I was going around generally during exam time, I often find people looking at the question and without drawing some kind of a diagram first. Okay, a lot of the time it helps quite a bit. You can draw some illustrations or diagrams just based on the given condition. Okay? Yeah. So that can help you thinking in 3D space, establish a sense. So, a couple seconds here, 10 or 15 seconds to go through that. And let's see what would be your answer. So let's just say first word. What do you think? Will the solution be unique? Okay, most of you say no, right? Okay, can you? So how would you illustrate based on the given condition? So maybe I'll just draw it here, see if yours is the same as mine. So what I did is I draw a vector n. Then because a vector is a free vector, so I'm going to draw this point P naught at here. Then I'll put them into one plane. Okay, put them into one plane. So you can always find the plane determined by this P naught and this n at here, right? Yeah. So, as a matter of fact, when I draw this plane, will that plane be unique? That's a side question. Will this plane be unique? So basically, giving a point and a vector n, are you going to have a unique plane determined by a vector and a plane? Think carefully here. This is actually vector is free. That's the key point. So if vector is free, will you have a unique plane solution? Actually, no, right? Because the vector could be here, could be here, could be here. The point is not going to move. So when you move the vector around here, think about that. Right? So anyway, yeah. But however, it's a different story though. If you're giving a line, okay, if you're giving a line and a point, you will have a unique solution, right? But even just based on my condition at here, let's just say, okay, how do I construct a line? So I can construct a line like this, right? And which is perpendicular to the plane. So that line will go through the P naught and perpendicular to this n at here, right? Yeah. And you can also construct a line which is passing through the P naught and perpendicular to that to the vector. That makes sense, right? So just based on this, I can have two solutions here. Okay. And as a matter of fact, if I move the a vector to somewhere else, right, I can have a different solution. Basically, the solution is actually going to be how many solutions? Infinite. Okay. Yeah. I think I just found out the mistake in my lecture notes. So anyway, always thinking in terms of the geometry here. Okay, before you start solving, right, and that can put you in a better position. Any questions? Okay, so we can basically we just wrap up that with the lines and the planes, so we can move on to a new topic. Okay, good. Okay, so now let's look at a new topic. We call that parametric equation, okay, of curves in space. So again, the wording, parametric equation, because when we're learning the line equation, so for example, for a line, if you have x of t equal to x naught plus t v1 and y of t equal to y naught plus t v2 and z of t equal to z naught plus t v3. This is the line equation. Or alternatively, this is the r of t equal to r naught plus t v vector. Okay? So when we learn line equation, I specifically said this is actually a parametric equation because this is in terms of parameter t at here, right? You can change the t to anything else. So line equation is a parametric equation already. Okay? And line equation, in short, can be written in this kind of format. So R naught is this vector. V is this vector. Okay, is this vector. So in short, we have this r at here, okay, which is basically representing this x of t, y of t, z of t. So the r, which is equal to x of t, y of t, and z of t. Okay, that essentially is the basis of this parametric equation. What you're doing is you're separating the x, y, z into three different expressions, right? Three different expressions. Okay. How we find expression is a different story, but we can have three different expressions, all in terms of the same parameter, and that's basically parametric equation or parametric equation. Not just for lines, we can extend the idea to any curves in 3D space, right? So for example, if I have a curve in the 3D space, okay, curve, then I can imagine myself there is a point P moving along the curve C at here, okay, moving along the curve C. So how do I represent the position of this point P then? I can use, okay, a position vector to represent the position of point P. So the position vector is a time function because as time changes, the P point will be at a different location on the curve, right? So that's why this is a function of t. As we're going to learn immediately, this is what we call a vector function, okay? Yeah, in the past, all you have learned is a scalar function. So function, for example, function of x, okay? Yeah, like that's scalar. Now this time, we're going to have a so-called vector function now. So that point P has a time-varying coordinates x, y, z. If it's a straight line, you can use this expression to represent the time-varying property of the point P. If it's some other curves, we will have a different expression for this one at here. Is that clear? Yeah. So that's basically the objective at here. We're going to try to find a parametric equation for some pretty common curves in 3D space, okay? Or sometimes just in 2D space. Okay? Yeah. So mostly we're going to look at this through examples. Okay? So let's look at the first example. Okay. And you will see the advantage, okay, of having a parametric equation describing a curve in 3D space. So first example is we have two planes. Okay, we have two planes here. If you look at the two planes given, and if you look at the normal vector, okay, normal vectors from the two planes, one is 1, -1, 2, the other is 2, 1, -1. Apparently the two normal vectors are not parallel to each other, right? So which means the two planes will intersect each other. If they intersect, you will automatically have a line at the intersection. Okay? So the question here is, what would be the line, okay, from the two planes here? Now, I think we had a similar question, solved similar ones. Probably, I don't remember if we solved them. But anyway, but I'm not going to actually solve that through the Euro approach. Okay? Yeah. So if you really have to solve that, then what do you have to do? You have to find a parallel vector to the line, right? And you also have to find a point on the line. So if that's the case, then you have the two normal vector cross product. You get basically the parallel vector to the line. And then you solve for certain intersection point because there are infinite number of intersection points. So you just need one intersection point, or one point satisfy two planes, and that'll be the point on the line. So you'll be able to get the line equation. Okay? However, we have a pretty quick way at here in terms of solving the line equation here. That's actually to create this parametric equation. So what we can do is we can do this, and this is also not unique. So I'm going to just let z equal to t. Okay, let z equal to t. If I let z equal to t, I'll put the t at here. Then what we're going to have is, right, we're going to have x minus y equal to 4 minus 2t, and 2x plus y equal to 2 plus t. Right? Yeah. Okay? And then, the next step I'm going to do is, I'm going to solve for x and y. So you have two equations here, right? You've got two equations. Consider the whole right side is known quantity. So solve for x and y, okay? Doesn't matter irrespective of what's over here, okay? Yeah. So in terms of giving this t at here, you solve for x and y. The two equations and two unknowns, so you should have a unique solution for x and y. Okay. Of course, the solution won't be a number. It will be a actual expression with a t in it, right? Yeah. So if you do that, you will see that this x equal to 2 minus 1/3 t, and y equal to negative 2 plus 5 over 3t. Okay? Was that good? Now, what do you observe at here? If I put the z equal to t back over here, what do we get? Line equation, right? That's a line equation. Is that line equation? Yeah. Parallel vector and a point on the line, right? Point on the line. Now this is actually the process, what we call is to parameterize based on the given condition here, okay? So this is the process of a parameterization. Okay, parameterization here. So I don't like an expression in terms of x, y, and I end up with three expressions, all in terms of one common parameter t. Okay, that's parameter. So now you can think aloud here. If you don't like z equal to 2t, if you do this, if you say, oh, I'm going to let x equal to t, and then solve for y and z through the similar process, guess what? You will end up with a different, right? Different line equation, but it is still the same line. Is that going to be the same line though? Is that? It has to, right? Because the two points intersecting each other. You can't have another line. So what's the point? The point is, you can have infinite number solutions for this parameterization actually. Okay? So there can be, just like a line equation, you can have an infinite number solution. If you change the point on the line, or if you change the parallel vector to the line, you can have infinite number solutions. Okay? Yeah. So you'll see similar examples just after this one here. Okay? And so what do we mean by infinite? Okay? Okay, so let's take a look at another example. So here's one, x squared plus y squared equal to a squared. Everybody knows what does it represent? Circle. What's the radius of the circle? 1? A, right? A. So now I'm going to create a parametric equation for this circle at here. Okay? Parametric equation. So there's no magic here, so I'll just write down the parametric equation though, huh? Yeah. But before I write it down here, still let's think about it in a physical point of view here. Let's just say I have a point P, and that point P is going to, okay, at the t equal to 0, okay, the point P is going to be here, and then it's going to move, okay, around this circle. Okay, it's going to move around this circle. As you learn in first year dynamics, it's going to rotate around the circle with an angular speed omega. Is that okay? Yeah. So rotational motion is going to move around the circle with the angular speed omega. Okay? Yeah. If it's going to move around the circle with omega, so technically what does that mean? So let's just say it started P at here, at a certain time T, it moved to this location. Okay, moved to this location. How much angle did it move? It probably moved theta angle, right? Theta angle. If the angular speed is omega, so what would be the theta then? Omega times T. Okay, times T. Okay. So now I'm going to do this. So look at this current location of point P. Look at the current location point P here. Okay, this is the P at T equal to T. Okay, at the current location. What is the coordinates? What is the coordinates of this current location P? Coordinates basically what's the x, what's the y value at T? Okay, great. So x equal to a sine theta, y equal to a cosine theta. Was that right? You sure? Second look. What's the x coordinate?
Oh yeah, that's backwards.
Backwards, yes. Cosine theta and sine theta. Okay? Yeah. Now, what we said is theta is omega t, so this is a cosine omega t. And this is a sine omega t. Okay? Sine omega t. Look at that. What's this one here now? This is x and y in one expression. So what we just did is, we end up with two expressions. And x is a function of t. And y is a function of t. So basically, we end up with a so-called parametric equation for the circle. Okay? So this is a parametric equation. Okay? Yeah. And what does this parametric equation describe? It describes a particle moving along a circle, moving in which direction? This is counterclockwise. So this is moving, so this describes a P moving, okay, counterclockwise, okay, at a speed omega, okay, at speed of omega. Okay? Yeah. So that's pretty nice because, you know, if you just say, hey, point P is on this circle, and you won't have any idea what kind of motion the point P is, right? But if you have this parametric equation here describing the motion of point P, and you immediately know that P is counterclockwise at the speed of omega. Is that good? Yeah. So now a similar question here is this. Let's say if the point P, okay, the starting point of point P is not here. The starting point of point P is over here. Okay, so let's say this is a B point and this is A point, let's just say. So if P, okay, start at, okay, B location, okay, at B location, and moving counterclockwise, and what will be the parametric equation for that point P? Right? So back to this original one here. So this one describes a point starting at here. Because why does it start at here? If substitute t equal to 0, what's the x coordinate? T equal to 0, cosine 0 is 1. So x equal to a, right? That's a. And we set a 0 here is 0. So that's why this at the t equal to 0 starts at this point here, right? Yeah. And now the question here is the P actually starts at the B location. So essentially, at the t equal to 0, the point P should be at the B location. So what would be a simple modification to the parametric equation right here? Switch the cosine sign. That's not very intuitive though. How would you do that? Very just simply. Let's say if I keep the cosine sign here. Pi over 2. What did you do? Did you plus or minus? It's a good guess though. A cosine omega t simply plus a pi over 2. Why pi over 2? Because when t equal to 0, okay, so what's the theta angle here? Pi over 2, right? Why is it pi over 2? What's the B location relative to the A location here? This is your x here. Your theta, right? Theta is always referenced to this horizontal axis. So at the B location, initially, what's the initial angle? It's a pi over 2, right? It is pi over 2, okay? Yeah. So all you need to do is this, okay? This. So a little bit further at here again, I want you to get comfortable with this physical meanings, okay? Yeah, not just the parametric equation. Yeah. But again here, if I look at the parametric equation of these two, what does these two parametric equations describe? They all describe what? The same circle, right? They all describe the same circle. If you tried it out, if you sub the x and y back into this equation, it doesn't matter if this one and this one here, you will end up with this x squared plus y squared equal to a squared, right? Okay? Yeah, so that's the point. So if P starts at A, but moving clockwise, okay? But moving clockwise. So moving this way now. So moving this way. What would be a suitable parametric equation describing that point P motion? Okay, what would be that? So this is an initial point P. So let's just say after a certain time T, it moved to here. Okay? Yeah. So what's the suitable candidate? Use the same similar approach. What did I do at here? I look at what? The coordinates of the point P here, right? The coordinate point P. Given this condition, what's the coordinates of the point P at this location? Exactly. So x over t equal to, first of all, x over t equal to what? To this, which is what? A times cos omega t. But y over t will be this portion, and that's what? A times sine, but where is this? It's on the
Below 0.
That's right. So below 0 we should have a negative here. Okay? Yeah. Is that good? Okay? So try to get used to this physical meaning of parametric equation. Alright? Yeah. Okay, so basically, again, you can see there are infinite number of solutions to here for parametric equation, right? So here comes another question. That circle happened to be located at the origin. So the circle's origin at the origin. Okay, the center is at origin here. So what if the circle has a different center, and the circle is centered at x0 and y0? Okay? If that circle is centered at a different location, and what would be the parametric equation for this circle here? Okay, for this circle. Can we come up with a solution or candidate for this parametric equation? So, always bear in mind is the parametric equation that you come up with has to satisfy the trajectory, okay? Has to satisfy the trajectory. Otherwise, that would be the wrong parametric equation. Okay? So given this equation at here, or given the trajectory at here, what can we do? If I think of this as a whole thing, the x minus x0 as a whole thing, just like this x at here. So that basically will give me what? X minus x0 equal to a, let's say, cosine omega t, right? And y minus y0 equal to a and sine omega t. So essentially, you can see is the y, the x and y, the x equal to x0 plus a cosine omega t, and y equal to y0 plus a sine omega t. Okay? Yeah. There you go. So this is a parametric equation for that circle, okay, at a different center other than the origin. Yeah. So simple question you should ask is, was that right? Yeah, well, if you sub the x and y into this equation, you can say your left side will equal to a squared. So that means that is the right parametric equation. Okay? Yeah. Okay? So just a food for thought here, just a quick question here, maybe you can think about for this. If I have a trajectory here, and suppose that I want to describe a point P that start at here and moving clockwise, okay, at a speed of omega, what would be a parametric equation, suitable parametric equation to describe this motion? So just like this one, starting at A, you use this, but now it's starting at this location here, okay? So what would be the parametric equation? Just think about that. Okay. For this motion, for this kind of motion. Okay. Any questions? All good? Okay. Let's look at the next one here. What we just dealt with is a circle. And let's look at this one. And this is what? Ellipse. Okay, it's ellipse. What would be a parametric equation for this ellipse? Okay. So you actually can use very similar way of thinking as a circle here. So in the circle, your x is a cosine. So in this case here, what we can do is very simple. Your x of t, a cosine t. Alright, if you want omega, you can let omega to 1 as t, right? And the y, what would you let the y equal to? Exactly. b sine omega t. Okay? Yeah. Now that's a suitable candidate for this ellipse at here, okay? For this ellipse. So the question is, you might wonder, is that right? Right? Well, how do you verify that? You substitute this one and this one, okay, back to this equation. See that if the left equal to the right, okay? And apparently, it is right. Okay? Yeah. And why did I say that? So anyway, in the end, right, so usually when we write the parametric equation, we don't just write like this. We can always write like this. We say R of t position vector. Because the parametric equation, remember, basically it represents is a parametric, a position vector. Basically it represents the position vector of a certain p on a certain trajectory. So the position vector is coming from these coordinates here, and that basically means a cosine omega t I hat plus b sine omega t and j hat, right? So this is the trajectory, or this is what we call, later we'll call this is the vector function, okay? Vector function. Okay? So what I listed it here, okay, the circle, the ellipse, and the next fuse are the ones I want you to remember, okay? And not just understand, of course, if you understand, you remember, but those are the ones that the typical curves that we'll deal with, right? Yeah. So the next example, y equal to x squared, okay, x squared here. How can we parameterize this simple equation, y equal to s squared? It's a parabola function, or basically it's this curve, right? How do we parameterize this guy here? What would be a solution, parametric equation for this one? Anybody give me a solution based on what we just have discussed here? Any solution is, what do you need? You need to come up with x of t equal to something, y of t equal to something, right? Okay?
Call yt.
What do you do? What did you just do?
So y of t must be t, and then x of t equals t squared.
Okay, so you just got it the other. So you're saying you let this one equal to t, and that's t squared. That's the right direction to think. But again, let's see. Does this parametric equation satisfy this given curve here? If a sub t squared here, sub t here, what's the t equal to? T to the power 4. So that's not going to be right? So how do I do that? Flip it, exactly. So, okay. Now usually, when you're giving a parametric equation, it also defines the range of the t, because we're going to do some integrals and derivatives, okay, with respect to the vector function. So usually you'll be given a certain range of t. So for example, if I say t, okay, is from 0 to 1, okay, that's generally how I write the range of the t. So if I just write t is from 0 to 1, can you plot out this curve based on this parametric equation and the given range? What would that be? So you start from 0, so what do? You sub the 0 to where? To here. So the point is here, right? Then you substitute the t equal to 1 over here. So 1, 1, and it's here. And what's in the middle here? That's the curve, right? That's the curve. So basically, you're looking at it starting at this location and moving up to this point at here, okay? To this point. That makes sense? Okay? Yeah. Okay, so now here comes the tricky one here, or just a twist. What if let's say this is A, this is B point. What if I want you to come up with, okay, this is A, this is B, okay, this is 1, and this is 1, okay? I want you to come up with a parametric equation describing a point moving from B to A, okay, instead of A to B. How would you write this parametric equation? Okay, the curve is this curve, okay? It's the same curve. How would you write the parametric equation? again, there can be completely different solutions though. Okay? Yeah. What would be a possible one? So this one describes this. Okay? Together. And I want a different one describing this motion. Okay, anybody? So what do you say? How about this? If I still use this, what should I do with the t's range? The t has to go from where to where? 1 to 0, right? Okay, so if you don't like this range, how come this t is starting from 1 to 0? Let's say I still want my t go from 0 to 1 though. Okay, so basically I say at the time equal to 0, that point P is at B. At t equal to 1, the point P is at A. Okay? Then what would be a solution for this parametric equation? Square root what? Y of t equal to square root of t, like this? Well, just looking at this one, it won't be right, because why, if I sub t equal to 0 here, where is the point? Y equal to 0, it's not going to be at the B point here, right? Yeah. So what you want is, when you're going to come up with a function, parametric equation. When you sub the t into that parametric equation, where are you? You are at the B location. That's the point here. Okay? So what would be a possible candidate? When t equal to 0, your x is 1 and your y is 1. At the same time, you had to satisfy this y equal to x squared. Oh, yes, I heard that. What would be, sorry, come on, louder? 1 minus t for which one? For x. Yes. Right? So, you look at it here, does that make sense? If I sub t equal to 0 here, x equal to 1, y equal to 1. If I sub t equal to 1 here, x equal to 0, y equal to 0. At the same time, does this x equal to here, y equal to this expression satisfy y equal to x squared? Yes, it does, right? Yes. Okay? So, this is the point here, okay? This is the point. Basically, parametric equation can be used very conveniently to describe a physical motion of a certain particle motion, so trajectory. It's not just a trajectory, but also the actual motion along the trajectory, right? Yeah. Because just y equal to s squared, you cannot describe a motion from B to A, right? Yeah. Okay. So that's the point. Now, just a food for thought here. What if I want t equal to 0 to 1/2 maybe? Okay, I'm moving from B to A. Okay, moving from D to A. And what would be the parametric equation? Okay, yeah. Think about that. Similar way of thinking though, huh? Similar way of thinking. You just have to do what? 1/2 right here, right? Yeah. Okay. Okay, so any questions? Okay, so this is a very common, very typical kind of curves. Okay, you will need to parameterize. Okay, maybe during exams. So you won't have a formula sheet for these things though, huh? Just I need you to know some of these very basic ones. Okay, so the next one, it's not going to derive anything, but I'll explain what this is. I have a parametric equation or vector function like this. Okay, so let's say we have a parametric function, okay, like this: x over t, y over t, and z over t. Okay, yeah. So what kind of a trajectory does this equation described at here? Spiral. Essentially, we call that this is a helix. Okay, this is a helix. Okay, it's very useful parametric equation, particularly in mechanical engineering and when we're learning basically in third-year schools, the thread of schools, the springs, right? And the way to construct that essentially is a helix. Why is it helix? We can look at this one here. If I just look at x and y, okay, just look at x, y here. As t changes, this portion describes is actually what? Circle, right? At the same time, when t changes, does that component is going straight up? Because when t increases, bt increases, right? So basically, you will experience a certain kind of a spiral motion or helical motion at here, okay? The helix. So specifically for this one at here, cosine t, sine t, what's the period that it goes one round? Or how long does it take to go from to go one round for this helix set here? When t equal to 2 pi, right? It goes one round. Okay, it goes one round. So the point goes one round. At the same time, it's going up by how much? By how much? bt equal to 2 pi b, right? 2 pi b here. Now this is basically, for example, it starts at here, it goes one round at here, 360 degree, and the vertical distance at here is this, okay, 2 pi b. And there's a term, we call that the pitch, okay, the pitch. So when you have a spring or you have a thread of the screw, there's always this concept, what's the pitch, right? Yeah. So that parameter defines the physical property of that component, okay, engineering component. Okay, so there's a maple file here. You can play around with it. Essentially, kind of the animations of the spiral motion. Okay, yeah. So now the spiral motion, actually, you should also be careful with this. Just like what we just did with the circle, right? Different way of putting the parametric equation, different speed. You look at this one here, I'm putting cosine and sine here, right? But you look at the circle we did is actually, did I put a cosine sine? Yeah, that's right, cosine sine too. Actually, you know what, if I change the cosine to sine, change this sine to cosine, would that also work? Yeah, that would also work, right? But the motion perhaps is going to be different. One way probably goes this way, and the other probably goes this way, right? Yeah. So bear in mind the subtle difference that are here. Okay. Any questions? So good? Okay. Okay, so probably the last one now, or the last two, so there's another one here. Okay. This is from the past midterm exam. Okay. So funny thing is, in the past, I talk about this during the class, and then in exam I may give exactly, more or less exactly, the same kind of question, and I still got lots of students have no clue of a constructing parametric equation. Okay, so I want your attention for this one here. Alright, so let's just say I have a point P at here, which is 1, 1, 0. Okay? I have another point Q at here, 1, 1, 1. Okay? The trajectory, okay, is from origin to P, then straight up to Q. Okay? That's the trajectory. And this is a curve, suppose the curve C. Okay, so constructing consists of two straight lines for the curve C. So maybe you can call this C1, this is a C2, okay? Can you construct parametric equation for curve C1 and curve C2? The whole point is essentially in the later class you will see that we're going to use parametric equation for integrals, for derivatives, for other applications, line lengths, arc lengths. If your parametric equation is constructed wrong, even if it's wrong very little bit, and the rest of the results will be all wrong. And that's how critical this is for the first step. Okay? Yeah. So C1, what's the C1 here? C1 is a point origin connecting P110. And if I look at from the top, essentially this is a P here, this is here. So C1 is part of the straight line at here, right? Part of straight line here. So that's C1. Okay. And what would be a parametric equation though? So unfortunately here, not like a typical math problem, you can follow a certain procedure to solve. And in this particular, most of the time, observation will lead you to the answer. Okay, you don't need to write down any intermediate step. You can just simply write down the solution in here. Okay, so R1 of t. And R1 of t has x of t, y of t, z of t. Let's start with the easy one here. What is z of t? 0. Good, right? So key hat. So then what about the y of t? Okay. So if you're not too sure, as I said, for this particular straight line, if this is x, y here, okay, what's the not parametric equation? What's the typical equation? X equal to y, or y equal to x, right? Yeah. So now you have y equal to x. Can you come up with a parametric equation now?
X equals t, y equals t.
Exactly. Would that be enough?
Yeah, see, t is between 0 and 1.
Great. So t goes from 0 to 1. Okay? That completes the parametric equation. Does that make sense? You have to verify, okay? Always verify, because if you're not sure, how do I verify? Verification meaning, does this parametric equation describe the trajectory C1? Which means at the t equal to 0, is that going to be at the origin? At the t equal to 1, is that going to be at the point P, right? That's how you do the verification. Okay? So if somebody disagrees with this, somebody says, well, I think it's going to be x of t equal to 2t and y of t equal to 2t. Would that be wrong? No. So what do you do with the t then? That's good. Okay? That's good. Okay? Okay, so C2. Again, let's do the obvious one here. Okay? So C2 describe another straight line. It's actually a vertical line from P to Q. What would be the most obvious one here? You have x of t, y of t, z of t. What is x of t? 0? X of t represents what information? Representing, you have point P here, representing what? The x coordinate of the point P. What's the x coordinate of the point P? 1. What's the y coordinate of the point P? Exactly. 1, t. Okay, so somebody asked 1, t. If it's 1, t, what's the t's range?
0 to
0 to 1, exactly, right? Yeah. So if you want to write everything out, essentially this is a z of t, right? You can write everything out, okay? Yeah. Okay. So that's actually the most common mistake is here, as we just did it here. Okay, lots of people put a 0, 0 here. Okay, yeah, lots of people put 0, 0. If you put a 0, 0 right here, your rest of the step all wrong. Okay, yeah, that's the danger. Okay, for this kind of mathematical problem. All good? All right. So bear in mind, parametric equation is not unique. Okay, and you can have as many possible solutions as you can. Okay? Now, what if, just one quick one here, so for C2, for this one here, this is a P to Q, right? This is a P to Q. Just a quick exercise like previous one. How about I want my C2, okay? C2 is still the straight line between P and Q, but this time I want it to be Q to P, okay? To Q to P. Basically, the arrow points down, okay? Points down here. Can you rewrite this parametric equation? So I don't think we're going to touch the x and y. How would be the z here? T goes from 0 to 1. Okay? Yeah. So understand the basic concept here behind constructing the parametric equation for the simple curves like a straight line, circle, and ellipse, and like y equal to x squared, that kind of situation. Okay, so this is basically the simplest ones that you could have in exam setting. Okay, any questions? It's all good? Okay, so the last one here probably won't be able to finish, but let's just start this one here, and it's more of just for fun though, okay? So we're going to look at the so-called cycloid motion. So what a cycloid motion is this? So let's just suppose that you have a circle. A circle initially sitting at this location here, and then you mark this point, this location as a point P. You mark, use a white spot like this. Okay. And then you start to move this circle, to basically rotate the circle. The circle not just linearly motion, but also rotating. Okay, the circle is going to rotate and moving along this direction. So then you trace the trajectory of that point P out, as the circle is moving along, rotating and moving along the trajectory here. Right? So if you do that, I'll just show you what it looks like here. Okay, so this is the circle right here, and that dot is the point P. If I run it, and you'll see that it traces out, this nice curve at here. That curve is called cycloid, called cycloid. So cycloid has many applications in mechanical design, for example, in particular in terms of gear, the tooth profile, and some other neat things there. So you're going to trace out something like that as a cycloid curves here. So the question is, what would be the parametric equation describing this cycloid curve? The curve here. I probably won't, I don't have time to solve everything here, but just give you some hints. You can look at the lecture notes here just for fun. Okay. So I'll curve out this cycloid here. At the same time, I'm going to draw a cycloid. I'm drawing the circle just arbitrarily suppose that at the t equal to a certain time, and that circle is over here. Okay? Suppose that circle is over here. Okay? Yeah. Then, as you can see, the center of the circle is not going to be moving up and down, so it's actually always right in this horizontal line right here. And the point P, okay, which is representing the motion of that marked point P, okay, let's say at that moment the P is here. Okay, so suppose this is a B point, and the circle always has a tangent point to the ground, and that's the A point, okay, A point. Then we can construct ourselves using vector concept. I'll create vector from here to here, from here to here, from here to here, and here to here. So close the loop like this, right? Close the loop like this. So you're looking for parametric equation. The parametric equation describes what? Describes the motion of a point P, right? Motion point P. Basically, the point P has x over t and y over t. Okay? So essentially, we're looking for a solution of this position vector OP at here. Okay? Yeah. So if you look at this one here, OP, which is what we're trying to find, given this construction, what does that equal to? OA plus AB plus BP. Okay? Plus BP. Okay? So if we can find each one of these vectors in terms of common parameter t or theta, then we are done with this parametric equation. Okay? So I'll just give you one hint here. Let's just say, what's OA? Okay, what's OA here? Okay, what is OA? OA, think about this, okay? OA represents the distance from O here. This is the distance. When the circle moves, your point P originally is here and move over here. So essentially, the distance OA is actually the same as what? That arc length of AP. It's like you have a string attached to this here. As P is moving, the string unwrap around this circle. So this distance actually the arc AP at here. Okay? And the theta, right, suppose it moved about theta angle here. So OA, basically, the absolute value OA is AP, arc length, which is A theta, right, which is A theta, because the radius is theta. And OA is a vector. O is a vector. If I want to represent the vector using x, y coordinate, what's that? X coordinate is this distance, the length, right? The length, which is A theta. What's the y coordinate for OA? 0. See, that's OA, right? Yeah. So, anyway, similarly, you can find AB and BP. So actually, AB is pretty easy because it's a straight line. It doesn't change at all, right? Maybe I'll just write on AB here. What is AB? AB has a length of how much? A. And what's the x coordinate for AB? Like this. Okay? Yeah, the only trick part is the BP. So anyway, check the lecture notes. But that's how you construct the parametric equation. Okay? Any questions? Just a reminder, first assignment is giving out, we should due on Friday, right?